So it is this business of nonlinear response, that is what we are going to deal with in some detail as we go along. Before we go there, I want to make a few points. I want to talk about the usual, there are the whenever we deal with Maxwell's equations at a introductory level, there are a lot of assumptions that we undertake without actually mentioning them. And the linearity, in the linear regime, that is, if I increase my E field 10 times, my polarization also, the response to it also increases 10 times. All right, so in the nonlinear regime, one could have a response of this kind, wherein you see that no longer the linear behavior governs. That is, if I increase my electric field 10 times, I might have a response of the polarization might increase 100 times. For example, this is what I have drawn here is a quadratic dependence. So such a possibility certainly exists. So the second assumption that we make in looking at typical Maxwell's equations is that of homogeneity. What that means is that my response functions, this susceptibility, chi, these are not functions of space, right? That is, my chi is basically a constant. Now, where does this come in is you will quickly recall that we had the Gauss's law, which was given in this form for the charge-free and the current-free regions. So here, this clearly implies the following, that my del dot epsilon naught E plus P. Equivalently, this is epsilon naught del dot E, which is of course certainly standard, plus what I get here is del dot of P is chi times E. Now you see clearly, if chi is a function of R, I have to be careful that, because now suddenly for this term I will start getting the gradient of chi of R. So that is what you neglect once you note that the medium is homogeneous. So homogeneity is one assumption that we make usually, and it is that homogeneity, if you go beyond that, then you see that this term will be non-zero. That is important. All right, so the third assumption that we make is that of isotropy. Clearly you see that my electric field is a vector, and it can have three different components. That is, my I can go from X, Y, Z, or 1, 2, 3 as you like. And this in effect creates the corresponding polarization, which would have three components. The most general scenario, you see that my susceptibility is actually a second rank tensor. That is, it has got now, in the most general scenario, 9 different elements. So you see, this is what I mean by something which is being, this is what is an isotropy. So when I demand that my chi ij is just a constant chi, in that case, this above most general equation reduces, that is, my x component in electric field generates a x component of the polarization. Similarly, y generates a y, z component generates a z. So you see, that is what essentially, so if I write it down in terms of a, so in my most general scenario, I can write down my P as a matrix with Px, Py, and Pz, chi xx, chi yy, chi zz. These are my diagonal terms. I'm setting the off-diagonal terms to 0 because my description of the susceptibilities along the principal axis. So this is the most general scenario. And in the case of isotropy, so when things are isotropic, what I'm noting is that my chi xx equal to chi yy equal to chi zz, and that chi is now a constant independent of the polarization direction of the incoming electric field. So that's another assumption that one makes. The last assumption that one makes is that of non-dispersive nature. Non-dispersive nature of the material. That is, my chi is again a constant, and so the non-dispersive nature actually is a very strong assumption that essentially violates in some sense causality. So let me just indicate that what in reality what happens is that if I'm looking at the polarization at some time t, then what I have is I have a response. I need to collect the response of the medium from all times, from minus infinity all the way to the time t. I need to now collect my response to the medium, right? Let me call this chi tilde. That is, in time, what I have is a convolution where every other time earlier than my instant at which I'm interested in contributes to the polarization at that instant. So if I say that something is non-dispersive, what I really mean is that the polarization responds instantaneously to the field at that instant. So actually in reality, if I go to the Fourier world, you see that my P of omega becomes now chi of omega times E of omega, where you see that each of these is the corresponding Fourier transform. That is, E of omega is a Fourier transform of E of t prime, E of t, P of omega is a Fourier transform of P of t, and this chi is essentially the Fourier transform of chi of omega is a Fourier transform of chi t minus t prime. So essentially this product in the Fourier space is equivalent to a convolution in the time space. So if I neglect this, right, in that situation I will make the assumption that chi becomes non-dispersive, or my system responds instantaneously to the stimulus. All right, so let us not get too much into this. From this, what I want to do is I will go to basically the nonlinear regime. So if I'm looking at the macroscopic polarization, you see that the macroscopic polarization is arrived at as number density of individual dipole moments, right? So P is the individual dipole moment and N is the number density of these dipole moment. This is microscopic in nature, whereas P is a macroscopic quantity. Now you see that so nonlinearity can happen in multiple ways. It can happen either through the dipole moment itself. Typically you see that the dipole moment of the particle is related to the electric field, or through the number density itself. We have already seen this business of nonlinearity arising out of number. You recall in lasers when we do, for example, we do pumping, what one is changing is that the electromagnetic field itself is going to determine the number of atoms in the excited state, thereby contributing to stimulated emission and so on. So you see that the number of players in the within the laser cavity, which we call as active atoms, are precisely governed by the electric field that is there within the cavity. So that's how this is, see that the nonlinearity is arising out of the number density. The other nonlinearity is that of arising from the relationship between the dipole moment and the electric field. So you see that roughly P, the dipole moment is linearly proportional to E. This is at low values of the magnitude of the electric field. So you see that E acquires moment, the magnitude of E, right? If it's comparable to the interatomic fields, right? That is, we are talking about the electric fields within the atom. These would be in the range of, let us say, from 10 to the power of 5 to 10 to the power of 8 volt per meter. When you are in this regime, this linear response breaks down. So in nonlinear optics, typically one writes down, so once you have this, once you have this generalized nonlinear response, one writes down the polarization in this very nice, compact and very instructive way. And that is that if I write down my ith element, that is, so I'm now almost certainly going to incorporate the anisotropy in my system. I'm accounting for it. So what we write down correctly as so chi ij ej. Remember, this is what is the linear response. And then you have the next higher order response, which is governed by a tensor of a higher rank. This is rank 3 tensor. And now you see that now we are started getting the products of fields plus chi 3 I j k l e j e k e l and so on and so forth. So that is the kind of nonlinear response that one usually gets. Now again, let me just remind you of this notation. The subscripts I, j and k, I, j, k, l, these take values x, y, z, and repeated indices implies a sum over. That is, if I'm writing down, so let me just look at quickly the first term. So for example, if I'm looking at px, right, involving, let's say, the first nonlinear term, okay, so let me just write down just that. So you see that I will have chi x is fixed, and then I have xx telling me this is ex, right? Then I have other term x, xy, which is ex, ey, plus I have other term which is chi x, xz, which is ex, ez, and so on and so forth. So roughly I will have 9 different terms just for the x element of the polarization. Absolutely similarly, I have to write down basically the next the y component and the z component, and hence I would get essentially 27 terms within the for the first nonlinear response, that is the chi2, or the susceptibility. That is the susceptibility of the second order. All right. Now, just some numbers, just to familiarize with what we are dealing with. So now if you look at some numbers, so let us just see what are the values of these higher order terms. So for example, I want to look at the typical values that you get for these quantities. So for example, the value of epsilon naught chi 1 would be of the order of 10 to the power of minus 12, all these in MKS units. Whereas if you look at the second order nonlinearity, that is epsilon naught times chi 2, these typical values range from 10 to the power of minus 24 to about 10 to the power minus 21, again in MKS units. You can clearly see that the units of all these quantities is indeed different, because they are multiplied by higher and higher products of the electric field. Similarly, if you look at the chi3, which is a third order nonlinearity, these will be of the order of 10 to the power minus 34 to 10 to the power minus 29, again in MKS units. So you see, this is what is the issue. To make these quantities are at least, as you go from one order to another order, there is at least a 10 order of magnitude difference. And in order to overcome this, one needs to compensate that by having strong electric fields. So it's only if you have significant amount of electric field strength that you would be, for example, if you want the effects to be comparable to the first order, then you clearly see that you require to compensate that extra 10 to 12 orders of magnitude through the electric field, so as to make this really comparable there. Now, of course, there are, one can still talk of smaller electric field where this continues to be a perturbation. So there are various regimes where different terms will become relevant. There is one important symmetry argument which I want to state. This essentially tells you about, so you see there are odd terms, that is chi ij, chi ijkl, that is the first order and the third order. Similarly, there is a second order, fourth order, sixth order, and so on. So you see that depending on the symmetry, one can actually make a very strong statement about these. So let us look at the following situation. Imagine my material medium is such that it is a system that is invariant under inversion. What I mean, that it is center of symmetric system. So what it means is that there is no preferred direction inbuilt into the medium. That would mean that if I come along the x direction in my electric field, I would generate the corresponding polarization along the x. And if I reverse the direction, let's say from plus x I go to minus x, I will invariably reverse also the polarization. That would mean that my polarization now becomes a odd function of the electric field. That is, if I'm going from R to minus R, I'm asking what happens. So if I'm looking at my polarization, so my polarization at minus of the electric field is same as the negative of the polarization of E, right? So if I put this, so let's look at the simplest of situations, wherein I'm looking at all the ij kl to be just to give you an idea of how this works. So you see that you can quickly put in there. So P of minus E, which I am saying is same as minus P of E. So clearly see, this demands that this should be same as this quantity, which is P of minus E, should be same as negative of epsilon naught chi1 of E. By the way, these are products, so not. So now if I compare these two equations, I will clearly see that my chi2 and my chi4, which is all even orders, chi6, all of these better be equal to 0. All right, so now we will look at the consequences of this nonlinear polarization on the wave equation. So let us quickly rewrite the wave equation. What you had was del square E minus 1 over c square dou square E over dou t square. This is a space-time dependence, and on the right hand side I have mu naught del square P over dou t square. Remember, the P is now contains, apart from other things, I can write it as a P linear. This is the term which is epsilon naught chi times E. So chi ij, ej if you like, this is the first term, plus P, which is nonlinear, which is the rest of the terms contributing to this. So you see, when I included the linear term in my polarization, only the linear term, what we got that our free space velocity went from c to c by n. Recall on the top we had got this n square is basically 1 plus the susceptibility, the linear susceptibility. So now, so once I get the linear part there, so if I substitute this linear and nonlinear paths like that, what I get is basically the following. I get del square E is minus now n square by c square. This is a contribution coming from the linear part of the susceptibility. And on the right hand side, I have a source term which can be written. This source term is basically mu naught dou square P, but now this P is the nonlinear P over dou t square. So you see, I have got a wave equation in which my right hand side has got a source term which is essentially being driven by this nonlinear polarization. That is, this higher order terms are going to drive the electromagnetic field. Right. Now you can clearly see there has to be, if one wants to solve this problem correctly, it would be important to realize that, remember that my source is a function of E itself, which in turn determines E, which in a circuitous manner again determines S. So you see, I have got this problem where I need to carefully calculate the E, which depends on the source, and where the source itself depends on the electric field, because that comes into the nonlinear polarization. So to solve this self-consistently, so there are two ways of doing it. One is iterative, more closer to the philosophy of Born approximation. That is, I first consider a field E naught. From there, I calculate the source term, which is based on E naught, which in turn determines my E1, because you see, now I have got a equation that is driven by the source term S of E naught. And then what I do is, in my next iteration, I take my E1, which is a solution of this new equation, and plug it back to get a new source term, which again helps me determine E2, and the journey continues. So that is so on and so forth, right? So this is the iterative mechanism. And so think of it pictorially. This is my medium. I come in with the applied field E0. Here I calculate the source term, which depends on E0. This in turn generates for me E1. And to this level, this is what is called as the first Born approximation. So, of course, one can do a more exact theory, and I will give you a glimpse of that coupled theory later. But in a sense, let me just first do it in a perturbative manner. And for that, I'm going to look at now the nonlinear oscillator model. So early on in the course, we looked at the linear Lorentz model. I want to quickly remind you of that. The electron, which is now coupled to the nucleus through a spring. Indeed, this is not the model for the atom itself, but it is a very good model for the atom-light interaction. In the sense that what one is claiming here is that in presence of the electromagnetic field, what you have is the electric field moving the electron either away or towards the nucleus, and there is an equilibrium position where the electron would like to be. And every time you add this perturbation or a drive of the external electric field, it basically the Coulomb interaction pulls the electron back towards its equilibrium position. So one can think that it is under a potential which is harmonic. So this you would recognize is half m omega naught square x square, or in other words half k x square, where k is the spring constant. So that if you think about the force which is being generated by this spring, it can be written down as arising from the derivative of the potential, and that is simply the m omega naught square x with a negative sign. Now we want to go beyond this. We want to look at the nonlinear response of the atomic system. We want to look at the nonlinear response of the atomic system. So what I have is that my potential is no longer harmonic. It indeed has this first term, which is half omega naught square x square, but it also has got higher order correction terms. That is some coefficient times x cube, and maybe another coefficient b times x to the power of 4, and so on and so forth.